Hello, everyone. In this video, we are going to study and solve related rates problems. Related rates. Consider a physical system of objects and rules represented by quantifiable functions, variables, and/or constants and related through physical laws and mathematics. Related rate problems deal with calculating the required or unknown rate of change of one variable using the given values and known rates of change of related variables. The following is a general strategy in solving related rates problems. First, identify the given values, known rates of change, and the required rate of change. Second, draw a figure with proper labels of variables together with their values and rates of change. Third, determine the equation relating the variables and the constants. Fourth, use the chain rule to implicitly differentiate both sides of the equation with respect to time t. Fifth, solve for the required rate of change by substituting the given and computed values and known rates of change into the related rates equation. Example 1. An unmanned aerial vehicle is being tracked by a ground station. The UAV is 2 kilometers above the ground and moves parallel to the ground at 5 kilometers per hour. How fast does the angle between the UAV and the antenna change 1.2 hours after the UAV passed directly above the ground station? Let x be the horizontal distance between the vehicle and the station, y be the vertical distance between the vehicle and the station, and choose theta as the angle between the vertical distance and the direct distance. The given quantity is the speed or the rate of change of distance traveled by the vehicle. The required quantity is the rate of change of angle when time is 1.2 hours after passing the station. The horizontal, vertical, and direct distances form a right triangle, which means an equation involving an acute angle and the opposite and adjacent sides is given by the following trigonometric function. As the vehicle travels horizontally, or parallel to the ground, the vertical distance remains the same. So, it can be replaced by the given vertical distance. Meanwhile, the horizontal distance changes, so it is still a variable. The strategy is to use the equation of the angle to find the rate of change of angle. The related rate problem is solved as follows. Take the derivative of the angle with respect to time. Because the horizontal distance changes as the vehicle travels, the horizontal distance is a function of time. Consequently, an inverse trigonometric function rule with the chain rule must be applied. Move the constant multiplier outside the derivative. Because the required rate of change of angle is at t equals 1.2 hours, the distance traveled during that time needs to be computed. It is equal to the product of the speed and the time of travel. Substitute the given and computed values into the equation. Therefore, the rate of change of angle between the vehicle and the station equals 0.25 radian per second after 1.2 hours of the vehicle passing the station. The unit of measurement kilometer divides out, so the unit of measurement is in radian per hour. The answer can be multiplied by a conversion factor from radians to degrees to get the rate of change in degrees per hour. A positive rate of change means that the angle increases as the vehicle travels in that direction at that instant of time. Suppose we have chosen theta as the angle between the horizontal distance and the direct distance. The inverse trigonometric function involving theta becomes the arctangent of the constant y over x. And then, follow the same steps as in the previous page. Take the derivative of both sides of the equation. Apply an inverse trigonometric function rule with the chain rule. And move the constant multiplier outside the derivative. Apply the chain rule again, or in this case, the general power rule. Because the required rate of change of angle is at t equals 1.2 hours, the distance traveled during that time needs to be computed. It is equal to the product of the speed and the time of travel. Because all the quantities on the right side are already known, substitute their values into the equation. Therefore, the rate of change of angle between the vehicle and the station equals negative 0.25 radian per second after 1.2 hours of the vehicle passing the station. A negative rate of change means that the angle decreases as the vehicle travels in that direction at that instant of time. Example 2. Two boats leave a dock at the same time in separate straight paths that make an angle of 60 degrees. The first boat is traveling at 35 miles per hour, while the second boat is traveling at 45 miles per hour. How fast is the distance between the boats changing after 0.8 hour? Let x be the distance traveled by the first boat, y be the distance traveled by the second boat, z be the distance between the two boats, and theta be the angle between the individual straight paths of the two boats. The given quantity is the speed or the rate of change of distance traveled by the boats. The required quantity is the rate of change of distance between the two boats when time is 0.8 hour after leaving the dock. It is not guaranteed that these distances form a right triangle. But because an angle and the length of two adjacent sides can be computed, try using the cosine law. The strategy is to use the equation of distance to find the rate of change of distance between the two boats. As the boats travel on a straight path, the angle between the two paths remains the same, so it is a constant. However, the distances change, so they are all variables. The related rate problem is solved as follows. Take the derivative of both sides of the equation with respect to time. As the boats travel, the distances they travel as well as the distance between them changes, so they are all functions of time. Meanwhile, the angle between the straight paths of the two boats does not change, so it must be treated as a constant. Apply the chain rule, specifically, the general power rule, and also the product rule. Divide out a common factor. And solve for the rate of change of the distance between the two boats. Because the required rate of change is at t equals 0.8 hours, the distances traveled during that time need to be computed. The distance traveled is equal to speed times the time of travel. The distance traveled by the first boat is equal to its speed times the time of travel. The distance traveled by the second boat is equal to its speed times the time of travel. Because an angle and the length of two adjacent sides are already known, use the cosine law to compute the length of the third side, or the distance between the two boats. Going back to the equation of rate of change of distance between the two boats. All the quantities on the right side of the equation are known. Substitute the given and computed values. Therefore, the rate of change of distance between the two boats is 35 miles per hour after 0.8 hour of leaving the dock. A positive rate of change means that the distance between the two boats is increasing in the given setup. Thank you for watching. Please like this video and subscribe to Professor Reginald's channel to get the latest updates.